Hi everyone, welcome to my lesson. Today's lesson is going to be on Introduction to Circuits. During this lesson, I'm going to talk particularly about how a circuit works, what are the components needed to make a circuit work, talk about some circuit characteristics such as what the battery does, the role of it, how do we measure the current, the voltage, the resistance. We'll look at current direction and different types of current direction and some other basic ideas of the circuit. So I'm going to go ahead and start our show. There we go, our slideshow. So as you can see in this image, you have a very simple basic circuit here. Now I usually call simple circuits with only one device in it. So you see right here, we have a light bulb connected to a battery, and this giant thing here is called the switch. And what a switch does, just like your light, your switch in your household, when the switch is open, the circuit doesn't work, and when the circuit's closed, it will work. So when you push this down, it completes the circuit right here. Although this is a switch, and you might use them in lab, I'll tell you that I'm not going to focus on switches too much in this course. Sound effects, huh? Okay, so like I said, I got to talk about all of these things: the functions of the circuit, the components, calculate the current in the wire, talk about direction of current, a lot of stuff to cover here. So normally what I do in class is I do this true-false exercise probably on Kahoot. So if we were to pretend it's class, I would read these to you and you would choose true or false. So why don't you do that just to see where your knowledge is in terms of your electrical knowledge right there. So take a second, pause the video, and go ahead and do this as true or false. Okay, so I think I hope you paused the video at this point, and I'm just kind of jumping in now. So to let you know that all of these are actually false. And we're going to go through each one of these basically for the duration of the class. And I'll explain what these mean and why these are incorrect as we talk about it. So a little cliffhanger here as we go through. So what's the minimum amount of materials needed to light a light bulb? So this would also be a classroom activity. So I know it's always tough to not do this. But I would give you a battery, a light bulb, and a wire, and I'd ask you to light it up. And then we would do another activity, which involves exactly that, the battery, the bulb, and the light. So you could actually do this activity if you want. I think it's still worth doing it by using the PhET simulation for DC circuits and see which one of these worked and which one of these didn't work. Oh, excuse me for a second. Just to see how, circuits work. I think it will give you a really good idea how to do it. And then I'd actually ask you and make predictions. Does the circuit work, yes or no? In this image, some of them do work and some of them do not work. So just FYI on that. But we're going to go ahead and get right into it. So there are 4 components needed to make a circuit work. And what a circuit is a closed loop at which charges continuously move. So as you can see in my image here, I have a light bulb, a battery, and all these little blue dots here. And we'll talk about what those mean as well. But in order to make charges move, my little thing here, ready? Actually, I'm going to go here because it's already here. You need 4 things for a circuit. You need a battery source or some sort of energy source. A lot of textbooks describe it as a pump. I don't like that. I think that's misleading. The battery doesn't make electrons. It certainly does push them. But it's an energy source. Very important distinction that this is an energy source, not a source of electrons, and more on that later too. You need something conductive around your circuit, and this is kind of one of those things that people get stuck on because you just assume this is the case. But just to be silly here, you can assume that, for example, you could use shoelaces to make a circuit. Not that you would actually do such a thing, I know that, but it is really important to bring that to your attention that you do need a wire in order for a circuit to work. You need some electrical resistance in your circuit as well. Now I put the word light bulb here, but that can actually be replaced by many things. In some other circuit terms, you can call this a load as well. But anything with electrical resistance. So a light bulb will provide electrical resistance. Resistors provide electrical resistance, but something to take away the energy of the electrons. It actually causes almost like a friction. Now I use the word there. Actually, I'm really cautious to use that word because it's not friction. In fact, you can get friction from moving electrons, but this is different. So I don't really like that word there, but just be mindful of what friction does in sense, and that means it slows things down. And then a closed loop. This is another one of those things if I asked you in class you would struggle on, because this is another thing you would just take for granted. Circuits have to be closed. They can't jump from one point to another. So like even going back to our original image here with our original circuit, if we just take a quick jump all the way back to the beginning, there we go. I actually should just put this in that, I'm going to do that. You're going to watch me do this live because I think I like it here. We're going to put that there and do one of these and we'll make it work. There we go. I like that. Okay. Let me back to this. Okay. So anyway, notice that there's a switch in here, right? So if that switch is open, that won't work. And that's essentially what you need. So you actually need all four of these. And if you're missing one of these, or if one of these, or two of these, it doesn't matter. If you don't have all four of these, it doesn't work. So let me just show you a few of these scenarios here. So let's see. So I have a basic circuit here. I'm going to take the current out for now because we don't need it. But notice that we have all of the parts that are needed for this to work. We have the resistance, we have the battery, we have the wires. And then notice we have the electrons. They're actually moving through this circuit. So let me do some silly things, although worth doing. Let's take out this battery. So I'm going to go ahead and just delete it out, but close the circuit. So as you kind of predict, you don't see those electrons moving anymore. The battery is gone, the source or that push for those electrons. I'm going to go ahead and put that battery back in. And as you saw with lab, I assume, is that as you increase the battery voltage, the energy of the battery, the faster those electrons start to move. This is a direct relationship in terms of the current. Okay, so let me be silly and make it open. So there you go. As you can see, the circuit doesn't work if you don't have a closed loop. In fact, we can even go more in detail with a switch. And there you go. Open switch versus a closed switch, right? So I'm going to close the switch for now. They used to have a really, let's see if they have, oh, they have other things. They do have all the things. Oh my gosh, I didn't know you could do this. I was like, oh, they used to have it, and they have it. So cool. Okay, so what I'm going to do actually now that I know that I have the things, will it work? Conductive material? It does! Fun fact, if you ever run out of your battery, this is actually a rechargeable battery, but let's pretend. If you ever run out of a battery and you're like stuck somewhere and you don't have 4 batteries for one of these, you could put a paper clip in one of the spots. I'll show you in class one day, if I ever get back to class, that actually does work. It's a conductive material. Does an eraser work? What do you think? Yeah, no. It's a non-conductive material. Will a coin work? Sure, it's a conductive material. What about a dollar bill? Dollar bill work? Nah, not a conductive material. So I'm so glad that they have this. Your hand? We actually have a lot of resistance, which is why in lab when you do this physically, that you actually won't cause the circuit to move, at least with this amount of voltage. You would be dealing with even smaller voltages, like 3 volts. So we actually have eternally along a pretty big circuit. Pencil. The graphite in the pencil is actually what's conductive, so a little bit, but not as much. Dog. I don't know why you put a dog in a circuit. I don't feel right with doing this, so I'm going to take it out. I'm curious with that. So, very cool. This is a much brighter light bulb. Very cool. Now I'm just playing. Very cool stuff here. There we go. High voltage battery. Interesting. And a fuse. Cool. Sorry. Fuses are cool. Let's go ahead and talk about a fuse since it's here. This is what your house is connected with, a fuse. So what happens is that when you have too much current, it actually breaks the fuse. I'm actually going to take that out. And I'm actually going to make the current so that it is larger than 4. So here we go. Oops, sorry. Oops, I did it by accident. See how it broke? That's how it fused. So when you blow a fuse in your house, the circuit is physically closed here. There it is. I took out the value. See? I'm going to reconnect it. Oh, too much current. Current rating is 4 amps. I have to fix this. So I'm going to put the resistance back up and then fix it. And there you go. So it's a safety thing. So when this current, let's put it down. So if I increase this voltage, I'll put this out here. See how the current right now is 0.2? Let's increase it until it gets to about 4. There it goes. See how it broke? And that's, again, a safety thing. So that's really cool that they have that there. Oh my goodness. I didn't know they had all that. Okay. All right, so anyway. I want to show you one more thing before I let this go. Take out this fuse. Okay. So the other thing I want to show you is what happens when you take this out and you just connect it, right? So here you go. So what happens is first of all, this is called an electrical short. Now the reason why it's electrical short, there's a couple reasons why we call this electrical short. One is the fact that if there's no resistance or something to take away the energy of these electrons, they'll just get faster and faster and faster and faster and faster and faster and faster, as you can see. Now, it doesn't actually cause the battery to catch on fire, but it does cause it to heat up. So if you've ever done this in class, I know, well, I've done it for many years in classrooms, but sometimes students will hook up 2 wires together without any resistance in a battery, and that battery starts to get hot. It gets to the point where it could burn you. It's pretty warm when that happens. So naturally, you don't ever want to do this. But this is also electrical short because there's no resistance. So that's another electrical short. Another electrical short, just to demonstrate what electrical short can be too, is if I did something like this. Say I had a wire and another wire, and I bypass that light bulb, right? Watch what happens. This is another electrical short. Now the reason why is because if I were an electron, I would not go through this light bulb, even though it's connected, because this is an easier path. Now I could get rid of the short and do that. So that's what it means by short circuit. Sometimes circuits are just old, and maybe like a piece of it falls, you know, a wire, instead of it going through the light bulb, maybe it goes here. And this is another short circuit. So this is a circuit short. But that's what happens when you don't have the resistance here. So all 4 of those pieces, the closed loop, there it is, the battery source, if this is 0, it won't work, the electrical resistance, which we just saw, and the conductive material. Those are all very important things to make the circuit work itself. So I kind of like this. I usually do this demo in class, so it's really sad that once again I can't do it for you. But I hope this makes sense. So I like to use the mailman analogy. Now, there's lots of analogies online that use water and pumping, but actually, I kind of like this one because it made me understand it a little better. So the mailman analogy is the following. So if you think about a mailman, right? They carry mail. Now, this is not mail, it's a tuning fork, but let's pretend. So the mailman is the electron in the circuit. The mailman, here we go. The way this thing is working. Oh, it must have, don't mind me and my everything that's open. For some reason, this thing must have, sometimes it times out if I don't use it for a while, so it gets mad. But here we go. Okay, so let's go back to my slides. Oh my goodness, okay, here we go. The mailman here is the electron. And of course, this is this person here. Now, I think this is why I like to use the mailman as the electron. So if you think what the electron does, right? The mailman goes through and makes a round, right? It goes through here. Now, what it's walking on is the conductive path, right? The sidewalks act as the conducting path. So the wire here is the sidewalk here. And yes, in reality, mailman can walk on other things. Well, let's pretend in this world right now that the mailman cannot walk on anything other than a sidewalk. If it's grass, it doesn't work. If it's water, it doesn't work. It has to be a sidewalk. That's what the wire is to this analogy. Now, the other very important feature of this is the energy. This is energy, the envelope. Envelope, there we go, envelope. Now, this is why I like this, because in the electron, it doesn't look like it's carrying energy, but electrons are energy carriers. So electrons carry energy. So, like the mailman carries the mail. But the mailman doesn't come with energy. It has to get it from somewhere, and that's what this post office is. The post office is the energy supplier. And that's what the battery is. So what the mailman does, he goes to the post office to get his envelope. He begins to walk around. When he gets to the house, what happens to the mailman? Does he disappear? No. Does he get more mail? No. He gets rid of the mail. He gives it to the house, and the house acts as our resistance, or electrical resistance. So this is like the light bulb here. The resistor takes away energy. So, thinking about it this way, the mailman goes to the post office, goes around the sidewalk, delivers its mail, and the electron leaves the house empty-handed. Now, I like this analogy because, as you know, the mailman doesn't get lost in the house or anything. It just leaves without the envelope. That's what happens to these electrons. They go into the light bulb, they give off their energy, and then they keep going back around, back into the post office to repeat. So the electron never goes away, and the electron gives energy to the circuit. It's an energy conservation. Again, if I have 9 volts of energy here, this is going to receive 9 volts of energy. It's conservation of energy. So I kind of spelled it out for you here. So you have it. And again, I don't like the word pump for electrons. It's the, I'm gonna fix this live on the spot here. So the electrons carries the energy. The mailman delivers the energy. The post office provides energy. The sidewalk is the conductive material for it. The light bulb receives energy. And then the closed loop, the mailman route. So the mailman typically follows the same route each day. And of course, obviously in reality, that's not true, but we're going to make it my reality because I can for this. Okay. So another thing I want to talk about is the role of the battery in the circuit. So a lot of people say when your battery is not charged, your battery is not charged, so it doesn't mean it has any charge anymore. That's not true. The battery gets re-energized. So what the battery does, so if you look at this image here, you have a fully charged battery and a dead battery. Now, if you look at the difference, in a dead battery, you can see the electrons are on equal sides of the battery, where in the fully charged battery, it's all the way on one side. So in order for the electrons to be pushed through this battery, you need an energy difference. Notice that if you have a pile of electrons on both sides, you're going to have the same energy on both sides, so there's no reason for those energy, for the electron to move. But if all the electrons are on one side, you make a lot of electrical energy there. An electron doesn't want to be next to all those electrons, so naturally it gets pushed away. It gets literally repelled. So because of that, just like we talked with Coulomb's law, because there's lots of charges here, it gets pushed. There's a force here, and that force is needed when you create an energy difference. So when it comes down to terminology, even though we say our batteries are not charged anymore, it's actually technically, it's not energized anymore. So that's a terminology, specific piece when it comes down to talking about batteries in a circuit. And again, it's really cool things I could do in the classroom. Unfortunately, I can't show you batteries, a dead one versus a live one. I could do it with a multimeter. This is unfortunately all the missed stuff you get in not having a class. Anyway. Okay. So we call the movement of charges an electrical current. In reality, the charges, we're gonna pretend that all the charges move in a nice straight line through a wire, when in reality they don't. We call it a drift velocity, but let's pretend here. So just like a river, in terms of flow, it's very similar, except instead of water particles in a river, it's charges in a wire. So it's very similar to flow rate, if you know anything about flow rate. In fact, to measure a flow rate, you need to know how many charges are flowing per time. That's what a flow rate is. That's the same thing with water flow, how much water is passing in a certain area per time. And that's what this is. We pick out a cross-sectional area, we count how many electrons are passing through. That's how you measure electrical current. The current is measured in a unit called amps, which is how much charge passes per time. And that's literally what this says, charge per time. As always, charge must be in coulombs and time must be in seconds. And coulomb per second is defined as an amperage or an amp for current. And that's exactly 1 amp of charge is 1 coulombs of charge per second, which is actually a lot of charge. If you think about it, I think it's 6.25 to the 18th electron, so that's a lot of charge. That's a big number. So let's go ahead and do this problem out. Most of these problems in terms of current are going to be pretty plug chug, so they're not going to be too difficult here. I don't know if that's a good color. We'll use black. Okay, so current is defined as charge per time. A steady current of 4.5 amps exists in a wire for 2.33 minutes. How much total charge passes by a given point, and how many charges would this be? So part A, we're given this value, so that is a current, so 4.5 amps. The amps tells me it's a current, or the fact that it used the word current before that. And notice that we know the current is going in some sort of time here. But I hope this rings a red, or raises a red flag because it's in minutes, not in seconds. So I need to convert this out to seconds. And the question is how much total charge. So we're looking for Q in this. So it looks like this. So 4.5 is our current, equals Q, divided by our time. So let's convert our time here. So 2.33 times 60 to convert it into seconds. So I'll do the conversion down here really quick, because in 1 minute there's 60 seconds. That gives me 139.8 seconds. So that number goes here. So to solve for Q, I have to multiply both sides by 139.8. That's because this was on the bottom here. 39.8. So 629.1 coulombs of total charge. But if I want to know how many electrons this will be, how many electrons, that's using the content from the previous lecture. So this is calculating the number of charges. So if I'm finding the number of charges, I have to take this and divide it. So there is 6, so this is part B, 629.1, oops, that should be a 1, coulombs of charge times, there are 1.6 times 10 to the negative 19 coulombs, oops, move my little picture, coulombs of charge for every 1 electron. Now, I should be official here. Technically, this should be negative, simply because we're talking about electrons here. And this is negative, and this is negative, which makes this a positive answer. So notice that coulombs cancel coulombs, and we just get E. So the number of electrons is equal to 3.93 times 10 to the 21st electron. So it's a lot of electrons. It was a lot of charge. 600 is a huge number for total coulombs of charge here. But yeah, that's the gist of this equation. And of course, as always, let me know if you have any questions regarding that. Okay, that's it for math for a little while. The rest of this is pretty conceptual. So a couple things I want to talk about too is current direction. So we're dealing with what's called as DC circuits. So DC circuit means direct current, which means one way. There is conventional and physical current. Conventional current is drawn from the positive end of the battery all the way around, as shown here. This models the energy of the system. This is what we will do. Anytime I ask you to draw the current of the system, we draw the conventional current. This is always, always true. I'm going to mention the physical current here because actually the electrons go the opposite way. The story goes, why is this? Why do we do this? It's confusing. Of course it's confusing. But back when Benjamin Franklin was actually studying charges, he thought positive charges were moving in circuits. And then he later discovered negative charges. So it was opposite what we thought was happening. So long story short, he messed it up. So now we, quote, fix it. And instead of measuring the current of the electrons, we measure in terms of energy. The energy starts from the top of the battery out. So that's conventional current. We will always use conventional current. I mention it because I want you to know in reality it does the opposite of how we model it. The battery polarity is huge when it comes down to direction of the current. So, so notice the way I'm doing this. This is in conventional setting. So the current would be labeled like this. It would be going clockwise, as you can see here. If I flip the battery, it changes the direction of the current. And the polarity matters. So polarity means which side is positive and negative. And you know this because if you try to put in your, if you take a remote and you try to put the batteries in any way, it doesn't work, right? The batteries all have to be in the same direction. Now, you notice that they're flipped like this. This just makes it more compact because you could do it, 4 batteries in a line, but then your object would be really long. If you want to keep it more compact, they flip it so that the circuit is much shorter and the object is much smaller. So that's the reason why they do that. But you know that you can't put these both in the same, like negative, positive, it won't work. So battery polarity matters. So here's the difference between AC and DC circuit, also that very famous band, right? DC circuit, as you can see, the charges all go in one direction. But the AC circuit, they actually move forward, stop, and move backwards. Crazy, right? So everything that's plugged into the wall actually is doing the alternating current, because that's where we get it from. Turns out that it's much, to make alternating current, it's actually much easier to make DC current. Alternating current is made by taking a magnet and spinning it. And because the magnet has a north and south side, it changes the direction of the current. But if it moves back and forth fast enough, we don't notice it. And in fact, that's true. It moves back and forth 60 times a second at 60 hertz. So I'm looking at my light, there's a lamp in the back of the room right there. We don't see it turning on and off because it's happening too fast for our brains to see. Fun fact right there. Also, another fun fact, we plug in our laptops, right? And if you ever notice on your laptops, you have like, I don't know if you can see this. I'll put it down for a quick second. You see these little charger things right here. Well, our laptops are DC. They run on batteries, but we plug it into an AC circuit. So that giant thing here, I called it a transformer. I really should have looked it up. I think that's the official name. But anyway, it has to actually convert the AC current to DC current because this machine does not run on DC. It can't, AC. It can't handle the shift of on and off. It actually has to run in DC. So it's a little fun fact for you there. But all of our things that are plugged in are rated to experience this, including our lights, our circuits, and all that fun stuff. Oops. Okay. So when it comes to drawing circuits, we're not, I know you're not going to draw circuits, it's just not going to happen, but I do want you to be able to read circuits. So there's hundreds of circuit symbols. I can go over so many, but obviously we're going to keep things simple here. So instead of drawing the physical things, it's sometimes easier just to draw their circuit components. So a battery positioned exactly the way it looks, with the positive here and the negative here, looks like this. It's going to have a long line and a short line. That, in fact, is a battery. Very important not to do this. This, in fact, is called a capacitor, and it's if you have them the same length. So it's important that you do that. That's the symbol for a battery. The long end means positive, and the short end means negative. If you have multiple batteries, this is 3 batteries, and I hope you notice that. That's what it looks like. The resistor is very simple. It's just a squiggle. And the light bulb is like a resistor, but we put the bulb around it. Now, I want you to know that there are so many different ways that people do this. This is the circuit symbol I like to use, but you'll see if you go on the internet, they might use this. It's fine. I just don't like it. Or they'll use, I've seen some circuits go like this and actually make the inside of the bulb like that. It doesn't really matter, to be honest, which one you use. I just want you to be familiar with them. So, for example, if we look at this, the circuit schematic, so instead of drawing the physical circuit, it would look like this. So the battery is actually upside down, so the longer one has to be on top. And this is a light bulb. Now, circuits are usually drawn boxy like this, not like what you would see in lab. In lab, it would probably look more like, I'm just going to clear the screen. In lab, you would actually probably see something more like this. You would have like the socket, and then you have the bulb, and then this would be attached to the battery, which would be then attached back like that. So notice, like in a real lab setting, it would probably be like this. So the reason why is because it's just much more neat this way, and we could put more things in here, and it's just more efficient. Sorry, I didn't mean to do that. So you could practice drawing a circuit schematic. So if you want to try it out by pausing the video, you can do that. I'm going to give you a second to do that. Okay, I hope you tried to draw this, and it should look like this. It's like that. Now, that's one correct answer. There are actually multiple answers, and it's just some silly things. So if you drew it like this and you put one bulb here and one bulb here, that's fine. It doesn't matter where the bulbs go. You put one here, or here and here, here and here. The bulbs don't matter. What does matter is this symbol, and the orientation of this battery does matter, because notice that this is positive and negative. So a couple other facts about circuits. So batteries don't make electrons. So that's a very common misconception. I know that when I was first studying circuits, I thought that were true. In fact, I would have put true on that questionnaire because, I mean, what else do batteries do, right? But no, they don't come in, they don't make electrons. And just like I was talking about before, light bulbs don't get terminated. They don't get eaten up by the electrons. So coming back to my circuit here, I don't know if you noticed before. Let's go ahead and make this a lot smaller so it's a little less crazy here. But I hope you noticed that when I was doing this, that when I was taking out this bulb, that the electrons in here are actually already there, as you can see. And then same thing, the electrons are here. So when it comes to where the electrons originate, they actually originate in the devices themselves, including the battery. Like if you take any of this out, you'll notice that there are electrons here. So we're just reusing those electrons that are in the material themselves. We're not getting them from the power company. We're not getting them from batteries. So that's one common misconception. And the other is, if you notice too, as the electrons pass through this light bulb, they actually pass right through. And if you follow it, you'll see that the electron keeps going. It doesn't actually disappear at all when it comes down to that. So that's one common misconception. So looking at that true false before, you would have seen that. Oops, didn't mean to do that. Okay. The next thing is the speed of the electrons. Same thing. When you flip on your light switch, it happens really instantaneously because they're already there. They don't need to come from somewhere else. You're not getting them from the power company or from the battery. As soon as you turn it on, the circuit works. And you know that if I put a switch in here, there's literally no delay. It works. But also notice that they're pretty slow. They don't move very fast, unless of course you make this silly strong like we've done before and make it like really fast. You can see you can get them moving. But they're not moving at this like lightning speed. They actually move relatively slow in the circuit. So that's another common misconception when it comes down to that. All right, so like I said, they're slow. They're already there. And last thing I want to kind of end with this video is Ohm's law. So Ohm's law is a pretty standard calculation in regarding the current. So as you might imagine, trying to measure the current by counting electrons per time is not a practical thing. You would actually, we had devices that measure current called an ammeter, and that's actually what this thing is right here. It's called an ammeter, am for amperage, and meter means to measure, so measuring current or amperage. But in this case, it's not practical. If you're designing a circuit, what you want to design for a certain current is to know how much energy you give and how much resistance you have. So that's essentially what Ohm's law is. Ohm's law is a relationship between voltage and resistance and relative to current. So like I said, when you're designing a circuit, you want to design it for a certain current rating, because if it's too much, like we saw in the beginning of the lecture, the circuit can overheat, right? And it can be dangerous in some cases. So that's really the practical thing. When you're an electrical engineer, you're required to do this. When I design labs, especially as a physics instructor, I have to make sure that I use the right voltage and current and resistance to, of course, to make sure things are safe, most importantly, but to make sure you see the effects in labs. So I actually use Ohm's law all the time to make sure that the circuits that I design work. Ohm's law is linear. There's no squares or square roots or cubes. So if you were to plot this, you can plot this two different ways. You could do current versus voltage or voltages versus current. It doesn't matter. Either way would give you a linear line, which represents the resistance of the circuit. And things that follow Ohm's law have a linear relationship or constant resistance. Resistors follow Ohm's law, but light bulbs do not, because over time light bulbs get hot, which changes the resistance. So that's why you get a curved notion with that. So I'll let Lab kind of talk more about the resistance in the Ohm's law. But more importantly, you can calculate values using all of these features. As you might imagine, the current is going to get higher if you increase the voltage. So if you use a stronger battery, the current flow will be stronger. You'll see the electrons move more. And I hope another factor is pretty straightforward. Is the fact is if you increase the resistance, the current's going to slow down. I think that hopefully that makes sense too, because as you add more friction in your circuit, the current is going to move slower. It's like adding, like if you think of a river, if you start adding more like obstacles like fallen trees or rocks and all that stuff, the current is not going to flow as fast as if you just had it wide open. So this is a direct relationship with voltage and indirect with resistance here. Now resistance is measured in the unit called ohms, hence Ohm's law. Voltage is convenient, is measured in volts, and current, as we discussed before, is measured in amps. So let me solve for you two more problems using Ohm's law. So I'm going to go ahead and do that. So Ohm's law says current is voltage divided by resistance. So while cooking dinner, Dinah's oven used a 220 volt line and draws 8 amps of current. So those are actually pretty accurate values, by the way. What is resistance? So our voltage in this is 220 volts. Our current is 8 amps. Therefore, we're looking for resistance. Okay, so the current is 8 amps. The voltage is 220 volts, and I'm looking for R. So if I do that switchy, which I like to do a lot, the resistance of this is going to be 220 volts divided by 8 amps. And I'll go ahead and do that calculation for you. So the resistance is 27.5 ohms. And there you have it. So I know some people are not, mathematically comfortable, so you can actually rearrange Ohm's law to solve for each thing. So if you want to find voltage using Ohm's law, it's going to be IR. And if you want to find resistance using Ohm's law, it's going to be voltage over current, like I just solved. 1, 2, 3. These are all different ways to solve the same kind of thing. Let's try the next calculation. Camille takes her pocket watch out of her bag and she gets ready for her homework. In the calculator, a 0.16 Coulomb charge encounters 19 ohms of resistance every 2 seconds. What's the potential difference in the battery? So first of all, I actually chose this question because of the word potential difference. Potential difference does mean voltage. And you'll see this all over physics because technically I skipped a whole section on voltage, which we're just not going to cover in our course. We just don't have time. But that does mean voltage. So anytime you see that, we can go ahead and look for that. So we're looking for voltage. Now, with Ohm's law, I have the resistance of 19. But notice I don't have current at all. I don't have current directly, but indirectly, I could solve current another way, right? I could do current as Q over T because we do have Q, which is 0.16 coulombs, and we have T, which is a nice convenient 2 seconds here. So what I'm going to do is solve for the current first by using the original definition of current. So let's go ahead and solve that. 0.16 divided by 2. Current's usually a pretty low number, so 8 is actually really high. I was so surprised with that other question. But 0.0 amps is pretty common when it comes to the current. So that's our current. So now that we have that, now we have it, we can go ahead and use Ohm's law to finish solving for this. So voltage is equal to, if you look at my note up here, IR. You could also plug it in here, both resistance and current, but you'll find that that is in fact true. So I is 0.08 amps, and R is going to be 19. Okay, 1.52 volts is our final answer. Ta-da. Okay, the second question is probably the hardest question you'll get in regards to Ohm's law. So if you don't have current, you can solve it using the other definition of current. So in your toolbox of things, you will have Ohm's law is one way to find current, right? And then the definition, this is called the definition of current, because in fact it is how much charge flows per time, but how much charge flows per time is dependent on the resistance and the voltage, like that. You can go crazy since these are the same. You could set them equal to each other, but we're not going to go into that. Okay. All right. This is Bill Nye the Science Guy. I grew up with him pretty much, and I learned a lot about science with him. You're not required to watch it, but if you're interested, it's actually a pretty good video. I would show this in class because it does a really good job of explaining where current comes from and how to get it. But I'm going to leave that for you to watch in another video. I'm not going to video and watch this demonstration here. Okay. You know, a good way to check your knowledge is to do this exit slip on your own. I would actually have you do this in class. I know I keep saying that. I'm sorry. But I would. What are the components needed for a circuit? What does the battery orientation do to the circuit or polarity? How do the components facilitate charge flow? Where did they come from, right? So just kind of answering these questions to summarize. The components of a circuit are closed loop, conductor, battery power source, a voltage source, and electrical resistance. The battery acts as an energy supplier for the electron. The conductive wire allows electrons to move. The closed loop allows the movement of electrons, and the resistance takes away energy. Without that, the circuit could overheat. The battery polarity causes the direction of current. So if I flip the battery polarity, it will actually go in the opposite direction, and it matters. And electrons come from the devices themselves. They do not come from power companies. Your battery doesn't make them. Once the circuit is built, they reuse the electrons in that circuit to keep going. So I hope that I answered all of the questions in here, and I think I did. Let me just take a look. So by the way, the chemical electrical cell means battery. So when the battery no longer works, it's out of energy, not charge. The battery can be a source of charge in the circuit. No, that's not correct. It comes from the devices. Charge does not get used up in a circuit. That's false. Charge does not go at high speeds. That's false. It goes slow. And the electric company does not supply millions of electrons per day. All right, I hope I've increased your knowledge about circuits. I'm going to extend that knowledge in the next video of series and parallel circuits, because once you add more than one device to your circuit, the circuit connections change what happens in the circuit. And I'll talk about all that in the next video. Have a good one. Thank you.